This is question 6 on the June 2013 AQA S1 paper. So we've got a normal distribution of sound in a bag modelled by a normal random variable with unknown mean and known standard deviation. So X is distributed normally, unknown mean, standard deviation 0.4. Sound in each of the random sample of 25 bags, so n equals 25, from a large batch's weight. The total weight of the sand is found to be 497.5 kilograms. So if that's the total weight in the 25 bags, we can work out the mean of the sample, x bar. So that's just going to be 497 divided by 25. So I've got a mean of 19.9 kilograms. So we want a 98% confidence interval for the mean weight of sand in the bags in the batch. So we're thinking about the mean weight of sand in the batch. So we're doing x bar, it's distributed normally. And we're going to use our mean from the sample as our estimator for the population mean, so 19.9. So right up here I forgot to put squared on my standard deviation, because obviously in our normal distribution we have the mean and then the variance. So for my samples, the means of the samples are distributed. We're going to use the standard deviation 0.4. We're going to divide it by the number of samples we've got, so that's 25. So that's our distribution for the means. So we want a 98% confidence interval, so I need to think about my normal distribution. I want 98% of the data. So when we're doing a confidence interval, we need to think about the shape of the distribution. I want 98% of the data in the middle. So I need to think about at the end, I've got 0.02% divided into these two parts here. So I've got 0.01 in each of those parts at the ends. So when I'm using my reverse normal table to look up the Z value I need to remember that I can only look up less than a certain value. So my probability of being less than a certain Z value here for my distribution is going to be 0.01 add 0.98. So I need to use the P is equal to 0.99. That's what I need to look up on the table. And if I look that up, I can see that the corresponding Z value is 2.3263. So now I'll construct my confidence interval for the mean weight of sand in the bags. So I'm going to do x bar plus or minus my Z value, 2.3263, multiplied by the standard error, which is going to be 0.4, the standard deviation divided by the square root of the number of items in the sample. Oh, sorry, that should have been 25. Just looking at the 4 from above. So 0.4 over the square root of 25. So I'm going to put that in. So my x bar was 19.9. So construct my confidence interval. So put my lower limit and my upper limit. And those two values then. And it says, giving the answer, it doesn't give me what accuracy it wants. So I'm going to use 3 significant figures. So 19.7 and 20.1. That's my confidence intervals for the mean. Next part says, hence, comment on the claim that bags in the batch contain an average of 20 kilograms of sand. So I'm going to look at my confidence interval. Does 20 kilograms lie within the confidence interval? So, yes, it does. So my answer for that part is going to be that 20 kilograms lies within the 98% confidence interval for the mean weight of sand in bags. So I'm putting it in context, and I need to then say, am I going to agree or disagree with the claim? So I'm going to say, therefore, I agree with the claim. So just making sure I put it in context, I've said if I agree or disagree. Part 3, state why the use of the central limit theorem is not required. Well, when do we use the central limit theorem? We use it when we don't know which distribution the underlying population is coming from. But if we look back at the start of the question, it says that the sand in a bag can be modelled by a normal random variable. So we do know the underlying distribution of the population is normal, therefore we don't need to use the central limit theorem. So weight of sand in bags, is normal. So I don't need the central limit theorem. Okay, so part B. Now we've got the weight y kilograms of cement in a bag can be modelled by a normal random variable. Mean 25.25, standard deviation 0.35. So we can write that down. Y is distributed normally 25.25 and standard deviation 0.35. So I need to square that because I've got my variance there. The firm purchases 10 such bags, so n equals 10. These bags may be considered to be a random sample. So that's the only way we can do anything more. Determine the probability that the mean weight of cement in the 10 bags is less than 25 kilograms. So firstly we need to think about what the distribution of the means is going to be. So y bar, the means, are distributed normally, and we're going to use the same mean from population, and then for our variance 0.35 squared over 10. So I've written down my distribution. Now I need to work out what's the probability that y bar, the mean weight in the 10 bags, is less than 25. So I need my z. So that's the same as probability z is less than, well, what have I got here? I've got 25, my value. Take away the mean, 25.25, divided by the standard error, 0.35 divided by root 10. So if I calculate that, my z value is going to be, so what z is less than minus 2.25877. So obviously we know it's going to be negative because 25 is less than the mean. So I'm just going to draw a little diagram to help me decide what I need to do next. So my z value's down here, minus 2.260. I want the shaded area that's less than that. So obviously I can't look up a negative value on my table, but I could just put it into my calculator. And if I did that, well, let's see what we get. So I need stat mode, shift, stat, distribution number 5, probability less than negative 2.26. So obviously it's a lot easier if you can do it on a calculator. And our probability is 0.011911. So round that up to 3 significant figures, 0.012. And finally, B part 2, calculate the probability the weight of cement in each of the 10 bags is more than 25 kilograms. So if I'm thinking about the weight in each bag, so that's in bold there, it's an important word, we're just looking at the probability for one single bag. So Y is less than 25. And then because I've got 10 of them, whatever that probability is, I'm then going to do to the power of 10, because I want 10 bags with the same. So I'm going to work out this probability to start with. Oh, sorry, I've put less than, but the question says more than 25. So let's make sure I change that. So actually, what's the weight in each of the 10 bags is more than 25. So then I need my Z value. Probability Z is greater than. So we're going to do 25, take away the mean, 25.25. This time divided by the standard deviation. So we're just looking at the Y distribution, so just 0.35 there. Because we don't have a sample. We're not looking at the means of samples, we're just looking at that. So if we work out that Z value, just do it on my calculator. Z is greater than, and again it's going to be negative because we're to the left of the mean, minus 0.7149. And I could just do that on my calculator, or I can think about the distribution. I want to use tables, so I want this less than, sorry, greater than that Z value, minus 0.71, and the diagram always helps. It's going to be the same as less than the positive value. So I want probability Z is less than 0.7142. So then I can use my table or my calculator for that. So that probability is going to give me 0.76247. So that would be the probability for one bag. I want each of 10 bags. So I need to do that to the power. So probability is going to be equal to 0.76247 to the power of 10. So for 10 bags, so the final answer, 0.06641. I'm going to give that to 3 significant figures, 0.0